Okay, again, we're going to solve this question without any numbers. And um, doing that for this particular question has two benefits. The first is you can apply, as soon as you see a question that's similar to this, you can apply this general methodology and then substitute in your values and get an actual number. The second reason is that you actually get some good insight into what the answer means by not having any numbers. Because with numbers, what tends to happen is the relationship between the variables gets kind of hidden, and therefore you don't actually get to learn anything about how the physics is working. So what we have here is three masses, M1, M2, and M3, and it's being pulled by force F to the right. What's interesting about this system is that we can treat this as one big block. And the reason is because they all must accelerate together. If they don't, if say M1 is lagging behind, well then the tension kind of instantly increases to pull M1 along, and that means that the tension force between the blocks is sort of correcting any laggards or any masses that are tending to go too fast. So if a mass goes too fast, for instance, then the tension force gets smaller. We get slack in our string, and that means that the force isn't being applied to the mass, and then it tends to get lag behind again, and so on. So it's kind of like it's a self-correcting type of problem. So what we're going to do is we're going to assume they're all together in one big mass, and let's just draw like a little dotted line here to indicate that that's happening. And we'll have this like be one big supermass. So right now what we're going to do is we're going to try to find acceleration. So on our supermass, our net force is equal to the force F only. So according to Newton's second law, the net force is equal to mass, and that's the total mass of all three of them, times acceleration, which is the acceleration of all the blocks. And therefore, if we're solving for acceleration, then we have F over mt, and then just recall that mt is equal to m1 plus m2 plus m3. So this is going to be a very useful quantity to us. So now what we're going to do is we're going to just treat each block separately. So bring back these blocks here. Oops. So right now I'm just going to focus on M1. And my goal here is to figure out what the tension force is between M1 and M2. There's another tension force between M2 and M3, and we'll call that T2. The force is going that way. So let's look at what's happening to block M1. So M1, it has a free body diagram that looks like this. Very simple, and the only force acting on it is T1. T1 communicates to block M1 the force F. So the way M1 feels force F is through this tension. So we can already get a sense of what tension 1 must be like, because there's been already, if force is kind of like, it has to be kind of parceled out to each of these masses. So some of the force is being applied here, some of it's being applied here, and some of it's being applied here. So the tension kind of relates the remainder of the force to M1. Okay, so let's do an FNet statement for this block then. Let's use a different color. So our FNet for block M1 is equal to T1, because that's the only force. And again, we'll use Newton's second law here. M1 times A is equal to T1. And A is equal to this right here. So we have M1 times F over M1 plus M2 plus M3. Now this here is very informative because it basically tells us that the force of tension is a ratio of this mass compared to all the other masses combined. And that's not surprising. If this is a very large mass compared to these, it will take up more of its share of the force F than the other two. And if this is less, then it will take up less. So this kind of confirms already what should be an intuitive idea of what's happening with the forces in this system. Okay, so let's look at M2 now. So again, what we're doing is we're breaking up. We're not looking at the whole system anymore. We're looking at each individual masses. And the reason why we're doing that is because the question is asking us for T1 and T2. And we have to look at each individual mass to get at them. So mass 2 is a little bit more complicated. It's got two forces, one going left and one going right. So T1 is going to the left and T2 is going to the right. Now notice before T1 was going to the right on mass 1 and T1 is now going to the left on mass 2. And that has to do with Newton's third law. A force is pulling on mass 1, but then we have to have an equal and opposite reaction force going the other way. So that's being applied to mass 2. So our Fnet statement, and I'll use a different color here, for this system is Fnet is equal to T2, and then I'll include direction, minus T1. Fnet is M2A this time. And then we'll bring over T1. And then we'll make our substitutions. So we have some pretty large substitutions here. M2 times A. Well, A is equal to this. So we have F over M1 plus M2 plus M3. And then T1 is equal to this right here. So that's M1 times F over M1 plus M2 plus M3. That's equal to T2. Now if you factor this out and simplify a little bit, what you get is, let's move this to the next page, is you get T2 is equal to F times M1 plus M2 over all of the other masses, or all of the masses. So again, this is telling us that the second tension force is a ratio of these two masses combined over the whole mass. And that makes sense because tension 2 is not only responsible for pulling M2, but it's also responsible for pulling M1. So it needs to communicate, it needs to be stronger than tension 1. So again, that tension 2 force is this. Now notice if you had numbers like a force and some masses, you could quickly calculate what the tension force is. And if you don't remember this formula or can't find it right away, then the process is you first find acceleration of the whole system, and then you break down each chunk. So you look at what the free body diagram is for M1, what the free body diagram for M2 is, and you solve for what you don't know and substitute in what you do.